All right, let's get started. So let's briefly review what we covered in the last Friday. So basically, in our last lecture, we covered the computation of the power spectral density for the line coding. And here's the description of the line coding scheme, right? So basically, this is a transmitted signal, right? And AK is kind of the coded message, right? For example, if it's for a NRZ code, a bipolar NRZ code, it will code 1 to 1 and 0 to -1, right? So those are the AK value. And PT here is basically the waveform that each binary bit will use, right? And so we can rewrite that as this, right? So basically, so we can consider this is our information message or our transmitted signal, and then before the transmission, we do a filtering using P of T here, right? And then, so basically the power spectral density is equal to this formula, right? So basically, this is we can consider this is our transmitted signal, and then this is the pulse shaping filter, right? And then this is the power spectral density of the real transmitted signal, right? And the goal is to compute this guy, right? And in order to compute this guy, so we need to compute this guy and this guy, right? So we know PT, right? And then, so PF is known, right? That can be easily computed. So the difficulty is how to compute the power spectral density of X of T, right? Which is given by this pulse train, right? It's a kind of train of impulses, and then each impulse will multiply by AK, okay, right? So basically, we spend our entire lecture to compute the power spectral density of X of T, right? And then, as we said before, so in order to compute the power spectral density, which is very hard to do, right? And then normally we compute the time domain signal, right? Which is the autocorrelation function denoted by Rx of tau, right? Where tau is the difference between these two signals, right? Time difference. Okay, and this is the formula to compute the power spectral density. So basically, in our particular case, because we have a special format of X of T, which is an impulse train, right? Given this structure, so we can simplify this formula to this one, right? So basically, this TB is the duration of a bit length, duration, right? And this Rn here is basically the autocorrelation function of the AKs, right? And here you can see that. So AK is a discrete time signal, right? Because all the A's are defined on integer value of K's, right? So yeah, and for this formula, we just assume that n is even value, right? And if n is not even, we just write 2n minus 1 till minus 2n to minus n to n here, and then put here 2n plus 1, right? Which is the same, right? Doesn't matter, right? So basically, in order to compute Rx of tau here, so the key is to compute Rn here, right? Which is given by this formula, right? And in our case, so we assume, yeah, we're going to see that later. Okay, so given all of this, so we can compute the power spectral density of X of F. It's given by this one, right? So basically, so this is Rn, and this is just the Fourier transform of all the deltas, okay? Okay, and then as we said, so Rn is an even function, right? And then so if it's even function, then we can break it down, right? And to cosine sine, and then the sine part got canceled because Rn is even. Then we just have this part left. Okay, so yeah, if you want, we can use the second formula to compute X of F. Okay, and as we said, the key is to compute Rn, right? In order to compute Rn, so we kind of have this two important assumptions. So the first assumption is that we assume the message signal UK, which are 0 and 1s. So they are IID. Basically, it means that they are identically distributed. So meaning that for UK and UL, they are independent, statistically independent if K is not equal to L, right? And the distribution of them are all the same. Okay, so and in our case, we assume that they're just a Bernoulli distribution with parameter 1/2, right? It basically means that the probability of UK equals to 1 equals to the probability of UK equals to 0 equals to half, okay? So yeah, that's a reasonable assumption. And the other thing is that we assume the system is ergodic. So basically it means that the ensemble average equals to the time average, right? So why it is useful? Because when we compute this guy here, right? So basically we assume that this is a clear time average, right? We assume the time average will go to the expectation of these two, right? And then computing expectation of these two would be very easy given the fact that all the AKs are IID distribution, right? Because the UK and the AK are one-to-one mapping, right? If UK is IID, then AK will be IID as well, right? So that's basically the logic. Okay, here are examples that we gave in class, right? So consider a bipolar NRZ code, right? So here basically we map UK equal to 1 to AK equals 1, map UK equals to 0 to AK equals to -1 here, right? And then we can compute, basically in this case, Rn would be 1 over TB when n is 0 and 0 otherwise, right? So as the part spectral density of Y is just given by this formula, right? Because Rn is just 1 over TB, it's very easy. And because we're using NRZ, it's a rectangle pulse shape, right? So the frequency, the Fourier transform of that is a sinc function here. It's a sinc function. Yeah, I think I forgot a square here, right? Should be a square here. It's a sinc function, and so with a phase shift, right? But if we square it, doesn't matter. So, and then this is what we got, right? So you can see it's a square wave, sinc square function. Okay. So yeah, this is basically what we got for the bipolar NRZ, and we didn't go very detailed into other line code here, right? But we do have it in our lecture notes. You can see the detailed derivation of it. So here are some examples, right? If you consider unipolar NRZ code, so basically it means that 1 map to 1 and 0 map to 0, right? Just have unipolar, right? If it's 0, we just transmit 0. And in this case, you may think, okay, so now we should have some DC component, right? With the exact same idea with this, right? In this case, you may think the Rn would be different, right? So the mean of Rn would not be 0 anymore. I mean, the mean of AK would not be 0 anymore, and then Rn will be different in this case. And if you compute that carefully, so this is what you got. It's almost identical as before, but the difference here, I think, is the DC component, right? So we have a DC component here. Everything else will be the same. I think maybe the constant is slightly different, right? Here constant is a squared. Here constant is 1 over 4 times a squared TB. Okay, the constants are different, but the shape is pretty much the same. And we have a DC component here, so which makes sense, right? Because it's a unipolar NRZ, right? Does that make sense? Okay, and then if we try something else, right? Let's try a oh no, yes, the next one. So let's try unipolar RZ code. Remember the difference here between the RZ code and NRZ code is that the RZ code is just narrower, right? So yeah, for NRZ code, this is the pulse shape, right? So this is NRZ. And for RZ, it'll be like this. Here is TB, right? This is the RZ code, right? Oh, yeah, it's unipolar, then just half of it, right? So we don't need the other part. So here's TB over 2, right? This is RZ code, right? And you can see that here. So the difference between the unipolar RZ and the unipolar NRZ is basically PF here, right? So everything, so this will be the same. Basically means that Rn will be the same, right? The only difference is the PF here, right? But here, because in the time domain it was narrower, then in the frequency domain it will be much wider, right? So basically, if you look at our lecture notes carefully, so you can see that so this equals to this, but it's the simplified version, right? If we do not simplify it, it will be equal to this guy plus a number of delta summation, right? But the delta location are 1 is here, and everything else is here, right? So it's in the 0 crossing point, right? They're gone. Okay, but now let's say if the waveform is narrower in the time domain, so it will be much wider in the frequency domain, then this guy will be wider, right? Then all the delta will be left. Not all the delta, some of the delta will be left, right? So which is the result here, right? You can see that all the delta will be the multiples of 1 over TB, right? If it becomes twice wider, then there will be 2 more left here, right? Still something will be here, but all of those will be left, right? Then equals to this guy plus the number of delta signal, and then multiply this guy. Okay, so basically, that's the power spectral density for the NRZ code. You can see there are a lot of this delta frequency component going on here. Okay, and finally, so we could compute the PSD for the Manchester NRZ code, right? Remember, Manchester basically for every for the waveform look like this, right? So this is a Manchester NRZ. Because it never goes to 0, right? And for this one, again, so basically for the AK, we map to 1 to 0 and 0 to -1. So this will be the same as the bipolar NRZ, right? So Rn would be exactly the same as the bipolar NRZ. So this is a formula to compute SY, right? And then the only difference here is basically this guy, right? And this guy is equals to like, yeah, I think, yeah, this guy probably is like, this guy equal to that, right? I say, so if we consider this is A here minus A here, right? And then we just divide it by TB to get SY, okay? So this is a way to compute it, to compute PSD. So is that clear, right? If anything is unclear, just look at my lecture notes, handwritten lecture notes carefully. Then I have all the details there, okay. Oh no, I need one more slide. Okay, let me see. All right, and today we're going to talk about a new topic. So I just want to show you this figure again. So basically now we know what to transmit, right? So, but it's just a transmitted signal, okay? So now we're going to focus on the receiver, right? So basically, you know, generally speaking, so all of this can be think as part of the demodulation, right? But in this figure in particular, I think demodulation only means that we shift the signal from the higher frequency to lower frequency, and then we're going to do some timing recovery, synchronization, and then we're going to do some MF means that match the filter, and some equalization. So equalization basically means that, you know, if we have some imperfection in the channel, then we need to get rid of this distortion introduced by the channel, right? So we're not going to talk much about equalization, and so we may talk a little bit on the match filtering. So, but the point here is that now we're going to pretty much focus on this part, right? To see, okay, how can we, after receiving the signal, how can we know it is a 0 or a 1, right? So those are our focus. And for the channel part, right? So the channel is between the transmitter and the receiver. So we assume the channel is a very easy channel. It just added a noise channel, okay? So it's called the AWGN. So we're going to explain what the meaning of AWGN. It basically means that the additive white Gaussian noise channel, okay? So we're going to talk about that in very detail today. All right. Okay, today is our lecture 31. Okay, so basically, yeah, from now on, so we just have maybe one or two big topics left, right? The big topic is called the detecting digital signals. in noise, right? So don't worry about the channel. We just worry about the noise in the channel here, right? And today we're going to cover at least what is the noise, right? So we're going to see how we can characterize the features of the noise, okay? And if we have time, then we'll start talking about the detection in the so-called AWGN channel. Okay, so this is our agenda. Okay, noise. Okay, so basically now let's consider a very simple communication system, right? Let's focus on still the binary communication system, right? So consider sending one binary symbol, right? So we'll give you a few approaches to send one binary symbol, right? Like the RZ, NRZ, unipolar, or bipolar, right? So consider, let's say, a bipolar case, for example. Let's see, we transmit a bipolar NRZ, so basically it means that let's say we transmit this for 1, right? And then I transmit this for, we transmit this for 0, and we transmit this for 1. Okay, and now let's say we send this signal through a channel. Okay, so we're going to send this signal through a channel with only additive noise. Okay, so what we mean is basically as follows. So let's say we send xi as either 0 or 1. Okay, and then we just add the signal with a noise denoted by n of t here, right? And then we do the demodulation and so on. And then we get, so our goal is to see which one is sent, right, as 0 or as 1, right? So basically we're going to determine whether y is 0 or 1, right? We're going to estimate I hat to see is whether a 0 or 1. So the reason I use hat here is that this is the estimation. It's the estimate of I. Okay. Right. So this is a channel that we will consider almost in the rest of the class. Right. So if we have time, when we talk a little bit on OFDM, then we're going to introduce the channel, the real channel in addition to the noise. But now, yeah, most of the part we just consider this channel, okay? So it's an additive noise, meaning this equal to noise add on to this, right? And so we can see that the noise here, n of t, so usually that is not deterministic, right? That's random, right? So if it's random and also it's a function of t, right, then we can model that as a random process. Right, so we say this is normally a random process. Okay. Did you hear what a random process is? No. So basically, you should know what a random variable is, right? So random variable is a function of what? Of the ensemble, right, is a function of the event, right? So basically now, so we model this randomness as a function of time. So basically, so t is another dimension, right? So for a given t, so that's a random variable, right? And just a random variable that is also a function of time. Does that make sense? Okay. Okay, so yeah, now let's see. Let's see how can we model this this noise. Okay. So before we see the modeling of the noise, let's see where does this noise come from. Okay. Where does NT come from? So in most of the part, yeah, we think NT is a thermal noise. Right? So what is thermal noise? So basically, it means that it's caused by the motion of electrons in the receiver electrons. Electronics, the receiver electronics, sorry. Right, so basically, yeah, we use Rx to represent receiver or receive, and the Tx to represent transmitter or transmit. Okay, and the reason that we have noise there is because normally the receive power is very low. Okay, so the receive power is very low. So normally that is on the scale of -7 dBm. Okay. And on this level, we'll see some thermal noise. Okay. So this is probably a direct part of the noise. Okay. And the other part of the noise is kind of not really noise, but normally, we can treat that kind of noise as the same as this kind of noise. So it's called interference. Okay, so normally the interference are added as well. Okay, so basically there are a few sources of the interference. Let's say, so now we just consider like point-to-point communication, right? It's like one-to-one communication, one transmitter and one receiver. Right, so yeah, we don't consider other case, because if you consider other case, then the model of the interference might be different. Interference might be different. Okay, and this is normally added, or is it aggregated? Okay, there are like a few sources of it. So one source is the sideband from adjacent channel. Right, for example, let's say we use FDM, frequency division multiplexing, right? We transmit multiple signals over frequency domain, right? If we don't have a perfect filter there, then there may be some leakage, right? Those leakage can be considered as noise. And the other one is, let's say, if we do not consider the one-to-one communication anymore, let's say you consider there are like lots of transmitters in a network, okay, and we consider there are a lot of transmitters, not only a few of them, a lot of transmitters, right? And then, maybe some transmitters that's far away from us will also introduce some noise, okay, like in a cellular system, right? If I transmit something to the base station and you transmit something to the base station, together with me using the same time, using the same frequency band, but you are far away from me, right? So you may cause a little bit damage on me, but not a lot, right? So those can be modeled as noise, okay? So the other source of it can be more distant users. On the same channel. normally we consider this is in the wireless domain, right? By same channel, basically mean the same time and same frequency. Okay, so those are some source of the noise. Okay, great. And now let's say, so given, yeah, now we know where does all the noise come from. So now let's consider, so how can we model the noise, right? So as we said, so we can model noise as a random process, right? And then what kind of random process? And let's see how we can model the noise, right? Yeah, let me write it here. Yeah, let's see the noise model. So basically, as we said, so we basically model the noise something like this, right? So we model NT as a white Gaussian noise. Okay, and here the important thing, so this is basically means WGN, right? And this A means additive, right? So basically the channel we introduced before is the AWGN channel. All right, and so we assume NT is a white Gaussian noise. Okay, and here you can see we have two components here, right? So one component is white, and the other component is Gaussian, right? Let's see what's the meaning of these two. Okay, so let's say this is A, and this is B, right? Let's explain those two one by one. Yeah, first one, what white, right? What is a white noise? Yeah.
Doesn't that mean it includes all frequencies?
Yeah, yeah, something like that. Yeah. So basically, it's an analog to what is white light, right? So what is white light? It has all the lights, right? So basically, each light represents a frequency component, right? White light basically means that we have all the frequency component of the light, right? So here, it's pretty much the same, but we define this because NT is random, right? So normally, we define this white in terms of the power spectral density. So we characterize the frequency domain in the power spectral density. Yeah, let's see the definition of it. So basically, white means that, it doesn't mean that in the frequency it has the same value everywhere. It just means that it has the same value in the power spectral density. Okay, same power density, right? So basically, white means that we have equal power spectral density at every frequency. Okay, so just like the white light, right? And in particular, so the PSD is given by this formula. So we use Sn of f, right? Hopefully you still remember how to characterize the PSD, right? So the PSD here is given by n naught over 2, where n naught is just some constant, right? Okay, and then for all frequency components. Again, so this notation means that for all. Okay, that clear? So basically, the PSD is a constant for all the frequency components. Right, in other words, the PSD is like this. Right, just a constant over all the frequency components. Does that make sense? Or no? probably not too much, right? Let's compute the power, right? Do you remember how to compute the power of the signal? Yeah, how can we compute the power? Given PSD?
Integrate it.
Yeah, it's a power density. The power is the integration of it, right? So we just the power, let's say we denote the power as Pn here, right? So it just means that we need to do this integration of our PSD SNF df, right? So clearly it's an integral from negative infinity to plus infinity, but it's a constant. So that equals to what? Infinity, right? That doesn't exist, right? So basically that's not possible in practice, right? Does that make sense? Right then, clearly, so it's not realistic, right? Because in practice, we cannot have a signal with infinite power, right? Seems too much. So then why do we still want this? Right? Why still want this?
The time domain would be a delta signal. You might be able to use that.
Oh, that's not realistic as well, right? Because that goes the magnitude goes to infinity, right? In practice, we don't have this. Yeah, yeah. It's kind of intuitive. So basically, the first reason is that, in practice, of course, this cannot go to minus infinity to plus infinity, right? And we don't care about go to plus infinity, right? We may care up to maybe, for example, like terahertz domain. So this is state of the art. Okay, above this would be like optical regime, right? So, but normally it's going to above this. In the optical regime, noise may behave very differently. But up to terahertz, so basically you can see the noise spectrum is pretty much flat, right? It's very close to practice, right? In other words, we may give a very big window on it, right? It doesn't matter, right? For simplicity, we just assume that in this way, right? Because it's very close to practice, okay? And the other thing is that in reality, the signals or every communication system is band limited. We don't have a system with infinite band, right? So in practice, basically, we're going to, for example, let's say it's a DSBSC signal, right? We just take a part of it. Just take a part of it and then get it out. And then this is the power of the noise, right? That's it, right? So it's so in practice, we don't have like this much bandwidth, right? So it doesn't matter, right? It can still be very close to practice. Does it make sense? Okay, and given this, so yeah, let's analyze let's analyze the autocorrelation function of the noise, right? So we know the part spectral density, so we take the Fourier transform, so we're going to have the autocorrelation function. Yeah, for this model, there are some very interesting properties of the autocorrelation function. Right, let's see. Okay, so we denote that as Rn tau. Okay, so that's the inverse Fourier transform as this guy, right? So what's your name again? Sorry. Eric. Okay, great. Yeah, as Eric said, so this is nothing but a delta signal, right? So it basically n/2 delta of tau. Okay. Okay. So now, as we said, so this guy is for a random process, right? Yeah, for a random process, normally we use RP to denote a random process, right? This is a random process, so the definition of the autocorrelation is, has to be in a random way, right? So basically, here we define an autocorrelation function for a random process. Let's say for a random process. So the autocorrelation function is defined in terms of the expectation, right? So before we see that defined in terms of the time average, right? So here we just define that in terms of the expectation. Okay, so it's nt multiplied nt minus tau, and then we do this expectation, right? That's the autocorrelation function in this case. Okay, so very nice. Okay, so now let's see. So this is the autocorrelation function, right? So maybe you consider that as a given, right? But now consider a random process, remember, right? So which is a function of t, right? So this guy is a function of t, right? But after the computation, so we can see it's not a function of t anymore. Okay, so basically, so this is very nice, right? So now we can see, so it's independent of time, right? So let's write it down. So basically, in general, so the autocorrelation function looks like this: RT and tau, right? It's a function of tau, which is the time difference here, and also it's a function of time, t. Okay. So, but in our case, so this one doesn't depend on time. Okay, so basically now we have our tau. So this basically means that it only depends on the time difference, or it only depends on how far they are separated, right? So basically, yeah, this means that it only depends on time separation of, yeah, if we consider each of them are samples, we just say depend on time separations of samples. Okay? So this is very nice. Okay. Of course, this is coming from our model, right? So we model that in this way. So we have this. Okay. And given this is the autocorrelation function of it. So basically, we can write the meaning of it, right? So basically, it means that when tau is 0, so that equals to infinity, right? And otherwise, it'll be equal to 0. Okay, so which is not realistic, right? Because when tau equals 0, it becomes infinity, right? And in reality, we don't have an infinity. And remember that, let's see. So when tau is 0, so this basically means that what? When tau is 0, this means the nt times nt, right? Let's assume nt is real. So basically it means that equals to expectation of nt squared, right? And what is that? Expectation of nt squared. Right? If it's not expectation, it's just a time average. Right? A time average of a signal square, meaning that is what? Right? Signal square, and then we do a time average, and we assume that goes to expectation. And the meaning of it should be what? The power, right? Because we do a time average. Right, this is basically the power, right? Which kind of makes sense, right? Power is 0, as what we discussed in the frequency domain. Does that make sense? Okay, yeah. So this is basically the meaning of white, right? White means exactly this. Okay, so now let's see, what do we mean by the second one? So what is the Gaussian? Gaussian, also called normal. Yeah, probably have seen this in your probability class, right? So basically, we assume the noise follow a Gaussian distribution, right? Given a fixed t, right, that will follow a Gaussian distribution, okay? So let's see what is the definition of Gaussian distribution. Let's say if n is distributed as a Gaussian distribution, right? So this basically means it's distributed as, right? So this notation means is distributed as, okay? And normally for Gaussian distribution, we have two parameters. We have the mean and the variance, okay? So basically, you can see Gaussian distribution is a very nice and simple distribution, right? It is only characterized by two parameters, which are the mean and variance, right? Let's see the meaning of the mean and the variance. So here, basically, the mean is the expectation of n, right? And so this is the mean, and the variance. What? Variance is the expectation of n minus the mean, and then we take the square of it, right? So this is the variance, okay? And also, if we break this square, and then we could compute the variance also equals to the expectation of n squared minus the square of the mean, okay? This is how we can compute the variance. Okay, and so this is basically how we characterize the Gaussian. Now let's see, so what is the Gaussian look like, right? So first of all, if we say it's a Gaussian distribution, so basically it means that n is a continuous variable, random variable, right? So n is continuous random variable, right? RV means random variable. And so this with probability dense function, or we call that PDF, right, as this one. So Fn of x, so that equals to 1 over the standard deviation, so which is the sigma here, right? And then we have 2 pi here, e to the power of x minus mu divided by sigma square, and then we take a half in front, right? So this is a PDF, right? You all know the mean of PDF, right? Right. So basically, you can get the true probability by the integral of it. Okay. So now let's be careful about all the notations here. So this is kind of important. So basically, this capital N means the random variable n, and this x basically means the value of n. Or maybe we can write this as n. Usually the capital letter means the random variable, and this small letter means the value of n, or the realization of n, right? So if that is the case, then we just write n here. Okay, and just remember, so the uppercase and the lowercase really matters here. Okay, so one means the random variable, and the other means the realization, right? And given this PDF, let's see how we can get the real probability, right? Okay, so basically, if we plot the PDF, we're going to see, so this is how the PDF look like. Okay, so it's like a bell shape, right? And now let's say, so this is, this value is the mean, right? So this is the highest point, okay? And so basically, let's see, Okay, so if we want to compute the probability that capital N is bigger than small n, let's say small n is here, so basically we're computing the area of this, right? So this area is probability of that guy. Okay, so that's basically the integral of Fn, right, from small n to infinity, right? So this probability equals to the integral of from n to infinity, and then we have our Fn here. Yeah, now we need to use a different dummy variable here, so like this. Okay, and then normally, do this, compute this integral is very hard, right? Because we have exponential and a square here, right? So normally the way we compute that is to look at tables, right? So there's a famous table called Q value, right? So basically, what we can characterize is that the probability that, or the area here. So basically, that is equals to the Q function. Okay, equal to the Q function. We use n minus mu divided by sigma, right? You can see, so basically what we did here is that we shift this to the 0 point because of minus mu here, and then we normalize it by standard deviation, right? Then you can imagine what does the Q function do, right? The definition of the Q function is as follows. So basically Qx, meaning we do the integral from x to infinity, but inside is a standard Gaussian distribution. That standard Gaussian distribution will basically mean that the mean is 0, the variance is 1. Okay, mean 0, variance 1, right? Therefore, we can see the inside PDF would be this guy because sigma is 1, right? So sigma is 1, then we don't have a sigma here, and sigma is 1 here, and mu is 0, then we only have like n squared left, right? So here, what we got is e minus x squared over 2, and yeah, we had to use another dummy variable, not x anymore. So I'll just use u here. Okay, this is definition of the Q function, and we can see, so this area is characterized by this. Okay, so remember this formula. So it's extremely important, right? Maybe next week you're going to start using this formula to characterize some of this kind of probabilities. Okay. Yeah, just be clear. So this guy is the PDF for standard normal distribution or Gaussian distribution, random variable. Okay, very good. Okay, I think we're almost time. Oh, just say one more thing. So Qx is also called the complementary cumulative distribution function or survival function. Okay, so that's the meaning of the Q function. And the other thing here, we can see that if the probability, let's say, is here is minus n, right? Then the probability of this n less than minus n would be the same as not minus n, right? So you know what I'm talking about, right? It's a symmetric thing. So basically, what's the value of here? Should be this guy plus this guy over 2. Let's see, x plus n over 2 should be mu. So this should be 2 mu minus n, right? Right, if let's say the n is less than the probability of 2 mu minus n because of symmetry here, so then this will be the same as that, right? Just be careful, right? Because with a Q value, you can compute this or that, okay? Okay, so we're going to continue in the next lecture. Yeah, thank you.